Hello, welcome to Cosmology Talks. Today we have Stuart Lyall, who is a PhD student at Swinburne University in Melbourne. You can tell it's in Melbourne because the sun's up behind me, and we're recording this at 11 a.m, which makes me very happy. He's talking today about detecting or constraining modified gravity models using peculiar velocities. In this case, using simulations of structure formation in these modified gravity scenarios to see what effects one might see in the real world. Although I suspect he might have some real-world data that he's going to show us today that wasn't actually in the paper. I'll let him talk about that. I find this interesting because, at least as far as I was aware, primarily historically these modified gravity models have been used as either the source or modifications to dark energy, but they should also change structure formation, and that's what Stuart will be talking about today. And they've kind of isolated the structure formation by fixing each model's background expansion to lambda CDM so that the effects they're seeing are 100% due to structure formation. And I guess in the era of S8 or sigma 8 tensions, this is quite interesting to me because maybe that tension is the first sign of a breaking down of the kind of lambda CDM plus general relativity structure growth scenario. So I'm keen to hear what Stuart might think about that as well. But do you want to start, Stuart, just by telling us briefly about the paper?
So we hope to further trying to distinguish different theories of modified gravity that people have proposed to try and explain dark energy and the expansion of the universe, specifically using peculiar velocity measurements.
Right. So if people are thinking of this talk or remembering it in 6 months' time, or your paper in 6 months' time, and there were only two things they were able to remember, what would you want those two things to be?
I want them to know that we can use peculiar velocities as an alternate probe into cosmic structure and dark energy measurements, or related measurements.
Just the one, or have you got a second one?
Yeah, no, it's probably the main thing I can think of at the moment.
Cool. No, it's even better that people only have to remember one thing. So no excuses. Awesome. Let's get into the background. Why did you do this? Why is this interesting? What questions were unsolved that you wanted to or needed to solve? Why did you solve them? And I guess why is this something we're talking about in 2023 and not a few years ago or a few years into the future?
So this is just the title of my paper, and I've been helped a lot by my supervisor, Chris Blake. The big question that we find ourselves is what is dark energy? Because the number that we've added on to the equation doesn't have any theoretical justification. The energy content that we have, it can only be found through experimental observation. A number of different theories have been come up with to try and explain dark energy. One of the common ones that floats around is that it's due to the vacuum energy of virtual particles and the fluctuations in the quantum fields. And other alternate theories have been come up with, such as some models where gravity interacts with higher dimensions of space that might affect its apparent effect on our more conventional four-dimensional space-time. All of these different theories are in play, and a lot of them have been kind of fine-tuned, or the ones that are further divergent have been disqualified, so that now that they all relatively closely follow the expansion history that we've measured. So it would be helpful to further distinguish between these models if we have another probe that we can use to differentiate their effects on the universe. Here's just a figure I've grabbed from a paper that's specifically discussing F of R gravity, which is another modified gravity model. But I'm just showing that there are regions of the parameter space which still need to be explored. I've also got some limits here placed by literature which constrain certain types of models.
So I guess you will define this F of R, because that was one of the models you looked into. You'll define this soon?
I've got that in a later slide somewhere. In my paper, I hope to provide another probe that can help distinguish modified gravity, which is peculiar velocities. So a quick run through of peculiar velocities. On cosmic scales, galaxies will be at a certain distance and they'll be traveling away from each other. And this is mostly due to the cosmic expansion of the universe as a whole. So much so that, the redshift due to the velocity of this expansion is usually directly related to the distance that we measure for distant galaxies. But galaxies also have an inherent motion just through their local space, as all objects in space do. And this is what we refer to as the peculiar velocity. which will add together to show the total observed velocity of the galaxy from our perspective. If you think of a simple linear situation where you have two galaxies just floating in the universe, over time they will attract each other with gravity and slowly tug on each other. And in that way, in a simple situation like that, you can think of that there would be a somewhat direct relationship between the peculiar velocity of these galaxies as they move towards each other and the strength of the gravity attracting them. This is actually very applicable to the cosmos at large, because galaxies have such large distances between each other on average that if you look at the large scale, at least, they don't have time to get near each other to undergo any other more complex gravity interactions and virializations and such. So on large scales, we can approximate that these peculiar velocities do have a direct relationship with the strength of gravity, which would be of interest if we're looking at different models.
Is this more linear than just, say, clustering data? That on the same distance scales, the peculiar velocities are more linear? Or are you just saying you are only looking at the linear regime? I'm just wondering about this bullet point saying they trace gravity in the linear regime makes it feel like you're trying to say that there are more linear probes than other ones, but maybe you're just saying you're only looking on the linear scales.
Yeah, I can't really comment on other measurement methods in detail. So.
Okay, but the point is that, because I guess peculiar velocity is on a smaller, like inside a galaxy, are very non-linear. But you're just looking at the linear scales, I guess, is the point.
Yeah, we're probably only looking at the galaxy interactions when the linear scale is dominant. Yeah, if things get too messy with non-linear effects, then yeah, specifically the models that I use in my analysis here would kind of break down a bit. So we've tried to avoid that regime.
I mean, maybe you will answer this, but it does make me curious about why one needed simulations. If things are still linear, one might assume one could do it, not pen and paper, but perhaps not having to run a whole simulation. But I'll let you answer that maybe when you get up to the simulations.
Yeah, the growth of structure is a important concept which appears in the study of these sorts of modified gravity theories, and it can be closely related to peculiar velocities. So the idea is that if we have a distribution of galaxies here, then in some regions you'll have a slight overdensity of matter, and in some areas you'll have a slight underdensity. Yeah, due to the forces of gravity, we expect over time for overdensities to become more dense because they attract other matter, and underdensities to become less dense. And this formation of clusters, is generally referred to as the growth of structure, which can be more formally described by this equation, where the delta is the overdensity and A is the cosmic scaling factor. Yeah, the growth of structure is represented by F there. And there's this linear equation, which has a few terms, but it shows specifically that the divergence of the peculiar velocities is directly related to the growth of structure in this regime. And then I also found this graph that does show that the growth of structure is expected to be at a different value for different modified gravity theories.
With this one, it's got data points on it. Are they actual data points or simulated data points from 2013? Or this graph makes it look like DGP and F of R are ruled out, right? Because they're not following the data points. But of course, there are free parameters in DGP and F of R that one can just make smaller, right? So it's not that all DGP models predict this blue line. It's that DGP with a particular parameter value would have predicted that blue line. Yeah,
this is showing modified gravity theories just at a bunch of example parameters that they have. Yeah, so they may not be representative of a well-fitting model. But yeah, I'm not exactly sure if that's actual data. It looks a bit straight to me, so check the paper again to see exactly what they're plotting there. But yeah, I'm mostly just referring to the fact that all the model lines are at slightly different values there.
Awesome. So yeah, let's get into the details. What are the specific models? What is this DGP and F of R that we saw on the previous page? How have you constrained them with your simulations? Well, not constrained, but looked at ways to constrain them.
So yeah, in my paper, just as a quick overview of what it goes through, I try and calculate theoretically from the theory of what these different modified gravity theories are to calculate some observable correlation functions that I'll get to later. And also, on the other side, look at, in this situation, simulations which use different models of gravity while they run to calculate gravity and the expansion effects. And from the simulations, we can directly measure these correlation functions as well. And then comparing theory to what we observe, I hope to recreate the input parameters that we've put into the theory side of the model so that we can recapture what gravity model the simulations used in this situation. So, my work at the moment is kind of proof of concept in this paper. So that's why we used simulations, because we can completely control the input of what modified gravity theory we're using. So in that way, we can compare the results we get out to the actual values of the simulation.
I guess in some ways you're then also testing that assumptions like linearity are valid, because the simulation will be non-linear. So if things deviated, then that might be why. I guess you've also probably got to have like a halo model and things in the simulation to have what is a galaxy and what isn't a galaxy inside the simulation. And so your theory stuff is also probably going to be you're testing whether you're doing that well on the theory side, I guess.
Yeah. So if non-linear effects kind of disrupt our kind of more linear model that we've got here, then we wouldn't get a good match at all. And so this whole kind of analysis would have to be kind of redone from the start if we wanted to get anything from it. These are the main three models of gravity that I looked at in my paper. I'm by no means an expert in any of them. I mostly just grabbed the equations that I could find and kind of use that to predict correlations through theory work and such. But the basics are that lambda CDM is what we know and love. It's got here's the action principle here. The F of R theory of gravity seeks to generalize the same lambda CDM action by having it as a general function of the Ricci scalar here. Though I'm looking at a specific model of F of R gravity, which is the Hughes-Sawicki.
So this might be an unfair question, given that you said you're not an expert on these, and then I'm immediately kind of asking you questions. But I guess the F of R model that you've written there is kind of maybe like a first order version of a model, because F of R has to reduce to R minus 2 lambda when R is big because of solar system tests, I guess. So one might naively think adding 1 over R is about the simplest term one could add, I guess, to have an F of R that does reduce to that.
Yeah, so as I understand it, it's more kind of seeing if we can find a generalized model that can fit. So it's more kind of coming from the perspective of altering the equations until we find a more complex function that fits, and hopefully that function, the form of that final function, would give us hints to what the concept behind it could be. I believe there's probably a bit more justification to some terms if you go into the actual theory. Like I think they get some justification from quantum mechanics and some particle interactions, but I don't know anything about that side of things. And DGP, which I alluded to in a past graphic, hypothesizes that there's a high dimensional space that gravity can interact with, which might in some way bleed the effects of gravity out as you get onto the large cosmic scales.
Maybe a naive question here, but in the DGP you haven't written R minus 2 lambda. Is that just because you've left it out, or is it assumed that the lambda is coming from the R5?
Yeah, that's the equation that I found, so I assume they're trying to account for it with that extra R5 term, but I can't say that for certain. And also within the context of my paper, which we'll come to shortly, these models here have a characteristic parameter, which describe a family of different specific models cosmologies that they can describe. And that's usually the parameter we're trying to constrain to narrow down what possible modified theories of gravity are actually real. So I use those parameters as kind of an input parameter to control how divergent from normal lambda CDM gravity these modified theories are.
So what is R naught then? Is that some constant that is unvariable defined by some, so the R naught squared in the f of r term. The reason I was asking is, I guess, just naively looking at the f of r equation, the time at which, or distance scale or magnitude at which that new term becomes relevant to me would depend on f of r naught times r naught squared. But of course, if r naught squared is some value that is given by higher principles, then yes, you're right. It's just f of r naught that, or f r naught that.
I think it might be just the average Ricci scalar value at current time. Alright, so yeah, I made use of a suite of simulated data that I was able to procure from Hans Winther. So I didn't create these simulations myself, but yeah, made use of the final data. And I had a bunch of simulations with different values for those characteristic equations down at the bottom there. So 3 different models for f of r and 2 for DGP and 1 for gravity. Normal lambda CDM in that situation. And so I had a bunch of correlation functions, which I'll quickly go over here. The first one is the galaxy-galaxy autocorrelation, which kind of shows what sort of scale distance you can expect galaxies to be at. There's the galaxy velocity cross-correlation, which kind of conceptually helps to describe the infall of galaxies towards other galaxies, or how much they pull and interact with each other. And also the velocity autocorrelation, which might help show the bulk flow that galaxies engage in as they travel through the universe. But largely, you might not need to have a fundamental conceptual understanding of what these equations are. The important thing for my work is that they are dependent on peculiar velocity, and so can be kind of used to probe the distribution of peculiar velocities, and in that way we can probe the growth of structure and how modified gravity theory affects the universe. So here's the theoretical equations that I've used to calculate these correlation functions theoretically for the different modified gravity theories. And they might look like a bit of a handful, but all of these parameters we can calculate from theory. And notably, the last one in that list is the growth rate of structure, which is that term I referenced before, which appears here in the equations. And you can see that this term is dependent on p, which is the characteristic parameter for the different gravity models. So that's where the different models will come in and change the equations.
Are these 3 equations essentially like very universal, like true, so long as you have the velocity given by the divergence equation you showed earlier, and then f defined by the growth of delta with respect to a kind of equation, and there's no actual assumption of gravity or even like Friedman-Robertson-Walker metric, perhaps. Maybe that is coming in because you've got a scale factor, but so how general are these equations?
So the different gravity effects would come into the growth rate of structure, but the rest are based off of the Friedman-Robinson-Walker metric. Technically, one area that my study might be fine-tuned is that I haven't taken into account how the different theories kind of affect the expansion rate. So if you went into a perfect recreation, then you'd expect the scale factor A and H to also be dependent on these models. But in theory, we're trying to fit to these models already kind of well fit the expansion rate. That's the area of cosmology that they're already kind of fit for. So we don't expect that to be wildly divergent from what we have.
And is that because I saw on the previous slide you had, little f r naught was 10 to the minus 4 or something, so I guess it's sufficiently small that the deviations from lambda CDM expansion have become negligible, but not still at the level of structure, I guess. Okay. And so here these P of Ks could differ between the 3 models, or is that kind of the P of K is the initial very early universe one that is the same for all 3 simulations, and the change is only through F?
Yes. In this situation, the power spectrum P is the same for all simulations. Yeah, it's been renormalized at the start of the simulation. And the top equation there doesn't have a growth rate of structure term in it, but we thought it would be important to include because it has this linear galaxy bias term, which isn't well constrained by theory itself, and so that's a parameter that we usually fit for through observation, and so that helps.
Sorry to just dwell on this P of K again. So you must have done something a little bit clever here, because if the growth of structure is different in the different models, if you start them with the same initial conditions, the final P of K would be different, and therefore psi GG would be different. So it must be that you start the initial conditions slightly different, so as that the late universe P of K is the same. Or am I just getting myself confused here?
Actually, I didn't explicitly put it in this equation, I don't think, but in my work I did include a growth factor term into the power spectrum.
Okay, so in principle this should be P of K comma P, as in like the parameters of the gravity model do affect P of K.
Yes.
A little bit. Okay, that's fine. That's what I naively thought. So.
Yeah, no, that's true. Yeah.
Okay, cool. So yeah, then it's fine if the initial conditions are the same.
Yeah. So the top equation has the linear galaxy bias in it, which helps break up the degeneracy that we might get between B and F. Yeah. So these two parameters, the linear galaxy bias and the characteristic parameter of the model that we're using. These are the two main input parameters that we need to experimentally fit for. So here's an example of these correlation functions that we've got here. The three different correlation functions are in the horizontal rows, and the vertical columns in this situation show the split up into the different gravity models here. And there's multiple lines for DGP and F of R because we have a number of different simulations with different input parameters for there. And so the points in this graph are found from observing the simulations, and the lines are the best fitting models with using those equations. And then it's just the old-fashioned chi-squared fitting to get to extract the input parameters P and B that we're looking for. And so then we've produced these posteriors to try and reclaim the parameters from the input cosmologies in the simulations. So the dotted lines represent the input values to the that were used in the simulations, and then the curved line is the relative probability of that value being the best fitting model theoretically.
So do you have some comments on this plot? Because there seem like a few things one might want to comment on. The red one and the blue F of R one look fine, but the other ones maybe.
I did discuss this with my supervisor. We thought that this was somewhat due to nonlinear effects, especially in F of R. There's a few nonlinear effects that even come into the linear regime that we might need to model with some sort of emulator to get a slightly more accurate correlation. And one thing that might also come into it, but on the right side, the posteriors are generally a bit wider, and that's due to the fact that the values that we've got on the x-axis here, the characteristic parameters, as they go to the right side in this situation, getting larger values, they become more convergent towards lambda CDM, and so the models themselves become less distinguishable between each other. So that explains why they're a bit more spread out on the right side compared to the left.
So this green and yellow on the right now, I'm much less suspicious about this than I was initially, because this is almost a prior volume effect, right? Because if 5, 6, 7, 8, 9, 10, 11, 12, 13, 14 are all indistinguishable, and if the data itself is, I suppose your posterior is going down to 0, so it is still a little bit suspicious. But the fact that it would just carry on forever to positive values because you're just getting further into lambda CDM, like that's definitely a prior volume effect rather than a meaningful thing.
So in the situation that we're looking at, a lambda CDM model, what we hope to do from this sort of analysis is to just put a lower bound on what these models could possibly be, because any measurement would disqualify higher, more divergent models on the left of this graph, and we'd slowly push the boundary of what are acceptable models further right towards a perfect GR lambda CDM match.
Speaking of nonlinear effects, did you try doing like a radius cut? Because on your previous slide you had the 3 correlation functions as a function of radius. I guess if you cut off the far left, that should cut out the nonlinear effects, or am I again being a bit naive?
Yeah, I forgot to put a slide in about this, but we did look at a range of minimum scale values. So these correlation functions are a function of r, which is the separation of the galaxies, and we didn't fit for values of this correlation below a certain scale, and because then you start to get the more complex gravity interactions and virialization of clusters and such things, which won't be well described by the linear theory that these equations I've got here are based off of.
It is also interesting in that this final plot here that the bigger effects, sorry, correct me if I'm wrong, but a smaller value of minus log 10 f of r naught is a bigger deviation from lambda CDM. So there it seems to be that your posterior is doing a good job, but when the values get smaller, I guess it's looking for more subtle effects.
Yeah, in some way we weren't as bothered about that kind of drastic shift at the bottom there, because they're starting to get so indistinguishable from each other. It's kind of reaching the limit of detectability between the limits that the posterior places and the input simulation.
Something's causing the yellow line to go down at 6 and not at 5. So it's seeing something in the data that's stopping it from being large.
Yeah, we also did a Fisher forecast, which is based purely off theory, where you kind of use the theoretically calculated cross-correlation matrix to predict the error bars that you'd expect from using this sort of analysis. And what's mostly happening on these graphs is that the solid lines show the expected error from a analysis applied to different modified gravity theories, and each has their own dotted line which shows the model that they're meant to be measuring, and if the error bar significantly goes below the dotted line of their model, then we would expect that this analysis would be able to detect positively that this model of gravity is being used.
So this plot was confusing me at first, but so would it be more correct to say that the y-axis isn't RC but is like sigma RC?
Yes. Yeah, and then I've just put some values down there comparing to the literature, and in practice we probably won't expect maybe the error bars to be this low. They might be a bit larger. I'm describing the constraining factor, so we're bounding the characteristic parameters, but I hope to show that this sort of probe into cosmic structure can be helpful in further constraining parameters. It is at least a competitive probe compared to other measurements made.
Are there potential issues on the observational side? Okay, maybe you can give the details about how you measure the peculiar velocity in the simulations, because I can imagine because we're God in the simulations, you might have been a bit sneaky and taken some shortcuts and actually measured the actual peculiar velocities, whereas in the real universe we've only got line of sight information, and the cosmological redshift is also there as an uncertainty. We don't know the lambda CDM model in the real world, so
yes, so we did play God a bit in here. We did take the exact peculiar velocities here.
So do you have an idea of how much that would weaken these plots in a DESI or other real world survey?
Well, we're getting a bit into what I'm working on at the moment, because we now hope to apply it to real surveys. Yeah, so the plots that I used in that paper, the paper that we're discussing, those didn't account for any observational effects. So that might not be a true representation of what you'd get from this model, but it's at least the purpose of the model is just kind of a basic proof of concept to show that this basic analytic technique and pipeline can be used to help probe the universe, and I hope we showed that we can reproduce a lot of the effects that are actually going on in the cosmos with these linear equations. So the main purpose was to show that we do well understand on these large scales, and can model the growth of structure in that way. But yes, in real models we'll have to take into account observational effects, which is my current work.
And also other cosmological parameters, in particular sigma 8, which might be very interesting. If the gravity is different, then the measured sigma 8 would be different for the same initial power spectrum, which is exactly what we're observing. So that might be something that, maybe in a few years' time when you apply this to DESI, you see that the peculiar velocities are slightly different to what we expect, and it's because of f of r, and that was the sigma 8 problem all along.
So I did tease you that I might have real data to show you from actually looking at real data and see if I can extract any information from that, but we're still working on it largely, and one of the things we are working on right now is figuring out how to apply sigma 8 correctly and account for that. So we have been started to take into account the visual effects, and fitting for real data. So using this method applied to real data, the 60F Galaxy survey and the more recent SDSS peculiar velocities survey, we've been able to extract actual parameters and posteriors from that.
Presumably their mocks are all lambda CDM mocks?
Yeah, no, this is just lambda CDM. And the fitting models that we used for the theoretical correlations here are just the lambda CDM fits, and we've also used the growth of structure just as a free parameter here to see if we can fit for that as well.
Mm-hmm. So f here is not f of our model. It's f being d log delta by d log a at that redshift. F can be It can be theoretically calculated directly from lambda CDM. So we have a expected value that we might expect to see from lambda CDM, which is somewhere between 1 and 0. So it looks like you're at the right approximate value, I guess.
If I remember correctly, it should be around 0.5. Yeah. So the real troubles that we're having at the moment, well, what we're working on, and hopefully we'll get through, is just getting the correlation functions to work for modified gravity theories.
It's very tricky for you that the mocks are lambda CDM, because you can't kind of test on the full mocks where you know the value of the modified gravity parameter to see that your method's working, unfortunately.
Though now that we've actually got the codes that can account for visual effects, I do hope to go back to the simulations and include visual effects there to get a better picture of what we'd get in that situation as well.
Yeah, so I guess we're already going into this in some detail, but where to next? Obviously, you've got these preliminary results you're already showing us. One thing I was wondering about is you did mention that if the linear stuff can't capture everything, there's the possibility of emulators. Maybe are there already like emulators of these f of r gravity and DGP with full ranges of parameters so that you can extract all of this information from a suite of simulations, or is that something that you need to tell Hans Winter to go and do?
I think we have briefly looked at some emulators for f of r. So I know that there are some out there that we can look into if our models aren't being very cooperative. In the future, after I've finished looking at real data, I was also thinking of investigating environmental dependence, such as whether galaxies are in tight-knit clusters or if they're in filaments or voids, galactic voids. Because, due to how the different modified gravity theories are affected by the distribution of matter, you might be able to get different distinguishable results from that. And so I've done some even more preliminary results for that kind of analysis. But I'll have to. That's just kind of an idea to go forward after we've got the real data working.
In some ways, one naively expects the effects of modified gravity to be the largest in voids, right? Because they're even lower density than the background density by definition. So if you've got this kind of curvature, 1 over r curvature term, and the curvature is the least in the voids, then that might be where the modified gravity is the largest. So even if the background and clustering statistics aren't seeing modified gravity, this might be where it's hiding.
Most of the models would be somewhat present in voids because they're all kind of trying to describe the largest scales. So once you get away from the galaxies and into regions where there's not strong potential wells and things, then all of these additional nonlinear screening effects that the modified gravity theory is kind of introduced to try and describe expansion kind of come into play. But unfortunately, galactic voids also are the regions of the universe with the least amount of galaxies for us to measure.
Yeah, I suppose if you just have a rogue galaxy in there, you can still measure its velocity with a high accuracy, although you can't measure the density because you haven't got as many, or the statistics of the density are much harder to measure. Yeah, so what work being done in cosmology at the moment do you think is particularly underappreciated by the rest of the community?
As a PhD student, I'm still kind of learning about the surrounding fields in cosmology that people are investigating, and acknowledging my own bias, I suppose. I'm interested in peculiar velocities, so I'll continue looking into that and hope to see if those can offer interesting insights into the universe.
Right, well, thanks everyone for watching. If you like this, please do subscribe and click the bell if you want to be notified of new videos, and click like to help with YouTube algorithms. It'll help you because YouTube will know to recommend more stuff like this, and it'll help the channel, and share the channel with colleagues. If you have any questions or suggestions, leave a comment. And thanks, Stuart, for the great talk.
Yeah, thanks for having me, Sean.